In this video, we will discuss the reaction quotient. By now we realize that most reactions are not a straight one-way reaction. They're actually an equilibrium, where the forward reaction and the reverse reaction both occur. And we write these equilibrium reactions using this double arrow. Now, how do we quantify this? Well, we use the reaction quotient. If we have some generic reaction, A plus B goes to C and D, with stoichiometric coefficients, then we can quantify the concentrations of the products over the concentration of the reactants using the reaction quotient Q, which is just the concentration of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. So if we go back to our old example, the equilibrium between N2O4 and NO2, well, the reaction quotient, QC, is just the concentration of NO2 raised to the power of 2 divided by the concentration of N2O4. A homogeneous equilibrium is one in which all reactants and products, and any catalysts if applicable, are present in the same phase. By this definition, a homogeneous equilibrium takes place in solutions. These solutions are most commonly either liquid or gas phases. So, for example, the equilibrium between hydrogen and iodine and hydrogen iodide, the reaction quotient is just HI raised to the power of 2 divided by the concentrations of hydrogen and iodine. The equilibrium between nitrogen dioxide and nitrogen monoxide and oxygen. And we can also show this in aqueous reactions. The equilibrium between silver ions and ammonia is just the concentration of the product divided by the concentrations of silver and ammonia. And finally, we have the equilibrium between nitrogen, hydrogen, and ammonia, which is just the concentration of ammonia raised to the power of 2 divided by the concentration of hydrogen raised to the power of 3 divided by the concentration of nitrogen. The other type of equilibria is heterogeneous equilibrium, and these are equilibria that also include solids and liquids. But because you cannot change the concentrations of solids and liquids, they don't appear in the reaction quotient. So in our first example, the equilibrium between carbon dioxide, carbon, and carbon monoxide, you notice that carbon is a solid. Therefore, the reaction quotient is just the concentration of carbon monoxide raised to the power of 2 divided by the concentration of carbon dioxide. In our second example, calcium carbonate, well, that is the only reactant, and that is a solid, so that does not appear. So this equilibrium quotient is just simply the concentration of calcium times the concentration of carbonate. In the next example, we see that we only have one component of the reaction that is a gas. All the others are either solids or liquids. Therefore, the equilibrium quotient is simply the concentration of hydrogen raised to the power of its stoichiometric coefficient. In our last example, the equilibrium between oxygen, hydrogen, and water, well, because water is a liquid in this particular reaction, the reaction quotient is just 1 over the concentrations of oxygen and hydrogen, hydrogen being raised to the power of 2. Now, we've been using concentrations to refer to the quantities of gases present. And this is perfectly reasonable because you can have gases at different concentrations because you can change the volume of your gases. But oftentimes we like to refer to them by their partial pressures. Sometimes in certain experiments they're just easier to measure. So we have a new reaction quotient, QP, which is in reference to the partial pressures of the gaseous components. Now QP and QC will be different numerical values for the same equilibrium because the concentrations and pressures are not identical. Now that we understand the equilibrium quotient, let's talk about the equilibrium constant. The equilibrium constant is the experimentally measured value when a reaction is at equilibrium and the forward rate of reaction is equal to the reverse rate of reaction for any equilibrium. So far we've seen the reaction quotient, but once our reaction has reached equilibrium, we use the constant K for the equilibrium constant. Now in this example we have shown with these subscripts that we have all of our concentrations at their equilibrium concentrations, but we usually don't show that. And so we can represent the equilibrium constant through either Kc, if we're talking about concentrations, or Kp, if we're talking about partial pressures. Now when it comes to comparing Q and K, well, let's see what happens. Here we have the equilibrium between hydrogen and iodine and hydrogen iodide. The equilibrium constant at some particular temperature has been measured to be 51.1. Now, under the following concentrations, will the reaction proceed forward, backward, or is it already at equilibrium? Well, let's take the equilibrium expression, Q. Let's take these starting concentrations, plug them in, being sure to square HI, and see what we get. Well, under these particular concentrations, the quotient of products over reactants is just 1.49. This is less than the equilibrium constant at this temperature under these conditions. So if Q is less than K, then the reaction must produce more product to reach equilibrium in order to balance this out. So this reaction will proceed forward. So if Q is less than K, the system proceeds in the forward direction in order to make up for the lack of product. If under these conditions Q is equal to K, well, that means the system is already at equilibrium and nothing's going to happen. It will proceed in its dynamic equilibrium where the forward rate equals the reverse rate. And if Q is greater than K, well, that means there's too much product. And in order to reach equilibrium and equal that equilibrium constant K, the system is going to proceed in the reverse direction. So far we've been presenting these equilibrium reactions from the point of view of writing them in one direction. However, because it's a dynamic equilibrium, the reactions actually occur in both directions. So there's nothing really stopping us from writing an equilibrium in the reverse direction. It's all a matter of your point of view. So taking our hydrogen and iodine reaction, here we have its equilibrium expression and its equilibrium constant Kc. Why not write it in the other direction? Well, what's going to happen? Well, what's this new equilibrium quotient? Well, we're just going to flip the products and the reactants from this new point of view. But this is also going to give us a new equilibrium constant, which we will cover in another video.